I'm Nikos, and this is joint work with my colleagues at ETH Zurich and UC Berkeley. So let me start the talk with an example. And nowadays, more and more clinics deploy remote monitoring medical web applications, which they use to remotely monitor the status of their patients. So you can imagine we have a patient that has some implant, like a pacemaker or some other kind of implant, and this monitors the patient status. And then through a local telemetry unit, it uploads some data to a remote server. This data might be, for example, a status of the pacemaker itself or status of the patient, like heart rate, EKG, and stuff like that. And then this allows a doctor in his clinic to access through a web interface this data about the patient. And based on what he sees, he might choose to take some action on the patient if deemed necessary. Now imagine what can happen if an attacker manages to compromise this server, this web server. Well, obviously, besides gaining access to sensitive information about the patient itself, the patients, he can also try to manipulate this information. And then when the physician accesses the web interface in order to read the patient's status, he can submit false data to the doctor. And this might lead to the doctor taking some wrong action on the patient, or maybe omitting taking some action that would be otherwise necessary for the patient's health. And depending on the use case, this might even be proven fatal for the patient. So integrity protection in this kind of settings seems to be quite important. And you can think also of other applications like in government, military sectors where decision-making is important. Then we would really need to make sure that integrity protection is there and we protect this information. So the problem at hand is how can we integrity protect and how can we provide integrity guarantees to web applications. And just to be a bit more specific, for example, now imagine that we have this doctor that accesses the web interface and wants to see the heart rate of a patient over time or the average heart rate of a patient over a period of time. And there are a few properties that we need to make sure that they hold. So first of all, we need to make sure that the result, what the doctor sees, is correct. So it was computed correctly based on what was submitted or reported by the pacemaker. We want to make sure that the result is complete, meaning that all the measurements within this period of time that the doctor asked were included in the result that is fetched back to the doctor, and also that the result is fresh, so that the result reflects the latest state of the application. So now we imagine that the attacker exactly can compromise the server, and he will try to serve back to the clients, to the doctor, for example, corrupted responses affecting all those properties, so correctness, completeness, and freshness, or either of these properties. And also, it's important to know that we don't quite trust the users of the application themselves, because now you can imagine a malicious nurse that tries to manipulate some data that she's not authorized to do so. And since we assume that the server is malicious, he might very well let her do so. So we need to make sure that this does not happen. And then when a benign client user of the application accesses this data, he sees the correct information. So actually, our security community has acknowledged this problem, and there is a lot of work in this field. So for example, just to name a couple of names, there has been work on file system integrity. For example, Sandra is a very good example and known example of this back in 2004. Database integrity, a recent paper called IntegrityB, but many, many other works before this on this field. And many of those papers introduce or make use of what we call authenticated data structures in order to protect the integrity of information. And again, those data structures come in various forms. Just to give you a couple of examples, it can be some sort of balanced Merkle hash tree or skip lists. And what they offer us, essentially, with these data structures, we can protect the integrity of a particular query run over, for example, a database. And actually, in our system, we do make use and build on top of these data structures. But given all this work, one might think that it's fairly straightforward to now migrate and provide integrity protection to a full-fledged web application. But there are quite a few challenges that we make sure we have to address, and then connect all the pieces together to make it happen. So first of all, web applications are quite dynamic. We have many, many users interacting with each other through the web server. And there is no single data owner, so different users are allowed to access and manipulate different portions of the website. And on top of that, since the basic means of accessing a web application is a browser, but it cannot be just like that, but this is a basic means, we cannot really assume any state on the client. A doctor might then go from another computer and try to log in for the first time to the web application. And also, the clients are not always on. And on top of that, we need to make sure that the developer of the web application will have some means of encoding the integrity policy of the application within the application logic. So we want essentially an API, to create an API that is generic enough and expressive enough in order to allow any developer to encode the integrity policy within the web application, and then at the same time, without changing or significantly changing his coding patterns. For example, we wouldn't now want the developer to change the way he writes the queries to the database. And this is exactly what we try to do with Verena. So Verena is a web framework for providing end-to-end integrity guarantees in web applications. And let me explain you shortly, at a very high level, how it works. So I'll try to give you, first of all, start with the basic components of our setup. Of course, we have our web server, obviously, and we also have our users. And the users have a private public key pair, and then they use this private key in order to, as I will show you later, to sign their write operations. So whenever they do some update on the data on the web server, we need them to sign the operations so that we can keep track who did what. Other than that, we assume a client-side web application setting where the code, the static code, think of JavaScript, HTML, CSS, and so forth, is separated from the data. So when the server sends these separately to the client, to the browser, and then the client-side code takes care of assembling this and rendering the page dynamically on the client. Obviously, we need to protect both of this information, both the static part and the dynamic part. Regarding the static part, there have been techniques already based on code signing that can allow a browser, before loading the web page, to verify that the code is untampered and authentic. So in this talk, we will focus on the dynamic aspect of the web application. So another important thing, as I told you, is that we need to ensure that whatever we get is fresh. But it has been shown already that if the server is compromised and the clients don't have any means of communicating with each other outside the server, so through another channel, then there is no way that we can have freshness, and the server can always perform fork attacks. So in order to solve this, we do need an extra component in our system that will help us ensure freshness. And this is what we call the hash server, and the hash server is essentially, you can think of it as a simple key value store that has a very, very simple logic, which boils down basically to telling him, put something, get something back. And it implements this narrow interface, and all we require from this server is that he doesn't collude with the main server, which is the server that is compromised by the attacker. So now that I have given you a bit of an overview of the parts of the application, so now let's assume that we have a pacemaker of a patient that uploads to the server some data about the patient, for example, the heart rate, periodic heart rate of the patient. And then the doctor wants, for example, to view the average heart rate of the last 3 days or something like that. There are a couple of questions we need to answer in order to make sure that what the doctor sees is correct and authentic. So first of all, is the result correct and complete? And essentially, this is exactly what the authenticated data structures give us, and Verena, as I told you, makes use of them. So the main server maintains balanced Merkle hash trees, and then whenever the pacemaker tries to update, for example, the heart rate of this patient, the server has to return back some proof to the pacemaker that he maintained, he updated correctly the tree to reflect the changes in the patient's data. And also, of course, the pacemaker will sign the root of the tree with his key, so that then we know who did the update. And then, in a similar fashion, when the doctor now accesses the data, reads the data through a query, then the server will have to return back a proof showing that the data reflects, so the data is correct and complete based on the proof, based on the tree. But the trees themselves are not, as I told you, enough to provide freshness. So in order to make sure now that what we see is fresh, we need to make use of the hash server. And as I told you, the hash server is more or less a key value store. And if now, for example, this tree that we see on the screen is identified by some ID, then the hash server will store the latest root hash of the tree in his database. And whenever the pacemaker tries to update the data that corresponds to this tree, then whenever the server returns back the proof, he will also return a freshly generated and authentic response from the hash server in order to prove to the pacemaker that the hash server committed the latest root hash as it was updated through the process. And in a similar fashion, whenever the doctor now reads the data, the server will have to fetch a freshly generated response from the hash server, showcasing that the tree and the proof that he got, that the doctor got from the main server is the latest one based on the latest root hash that is stored on the hash server. And finally, even if all this checks out, we still need to make sure that the result that the doctor got was affected by authorized users. So how do we know that this pacemaker is supposed to be manipulating this data for this patient? And in Verena, we introduce the concept of trust context, which essentially is the group of entities that are allowed to affect the results of some query, of some read query, meaning that they are allowed to manipulate the results that are relevant, for the data that are excuse me. It's a group of entities that are allowed to manipulate the data that affect some query that we want to run. So in our case, it's clear that the trust context for this data, for this heart rate of this patient, the trust context is the pacemaker. And now, if we have a nurse that tries to update this data, and the server is malicious, so he might as well allow it. Our notion of trust context will make sure that when the user's browser fetches the data from the server, he will identify that there was some unauthorized party that manipulated the data, so he will warn the doctor that something is wrong. On the other hand, if for the sake of this example, we assume now that the nurse is part of the trust context, then she's also allowed equally well as the pacemaker to manipulate this data, and then our system will check that everything is okay and everything will check out. So in Verena, each query runs within a trust context, and then you can imagine that trust context is associated with some authenticated data structure, which will provide us with the properties that we need. But also, what is important is that, and this is explained further in the paper, we have the ability to run queries over multiple trust contexts that we don't know beforehand, but still we can ensure completeness over that query. In other words, ensuring completeness over multiple authenticated data structures. And of course, we have an API that allows the developer to manage trust contexts, like, for example, creating trust contexts and inserting or removing members. And also, the developer now will have to use some sort annotations in the code in order to tell Verena which queries need to be protected and which queries need to be protected using what we call integrated query prototypes. And then what happens is that our system takes care automatically of whenever a developer writes his queries, automatically in the background identifies and maps the query to the correct trees that have to be maintained and to the proofs that have to be updated and fetched back and forth. So transparently to the developer without having him worried about this. So we wanted to implement Verena and evaluate it. So we chose Meteor, which is a popular client-side framework, in order to implement it. And essentially, we implemented Verena as a Meteor package. So Meteor is a Node.js-based product, so everything, or almost everything, runs in JavaScript. But we did implement a Chrome native client application that runs within the browser in order to speed up the public key operations in the browser, because otherwise, with JavaScript, it's a bit slow. So this was roughly 5,000 lines of code. And then for the hash server, which I told you, in any case, his logic is quite simple. We used Golang with OpenSSL, again, because OpenSSL is quite faster than the Golang implementations of public key crypto. And the total lines of code that we needed to write was roughly 600. So we used our implementation in order to evaluate Verena. And what happened is that we were given access to a real remote monitoring medical web application used by clinics. And we re-implemented its basic functionality in Meteor. And then we used Verena on top of it in order to integrity protect it. And then we wanted to measure the latency. So for example, how much time it takes for a doctor, for a browser to load a web page that is a view that the doctor sees commonly in order to view some information about the patient. And as you can see, for the maybe heaviest views, so the second view, for example, the total time, the latency can be up to 82 milliseconds on average. Now, if we compare this to the vanilla Meteor implementation, meaning that Verena is not enabled, then we can see that it's an order of magnitude faster, the vanilla version. As Christina said, there is no free lunch, so there is still some overhead. But the important thing to notice is that even with these timings, the user experience should not be affected. So still, the doctors would not experience something different in their browsing behavior. We did also some other measurements as well, and feel free to read the paper for more results. So to sum it up, with Verena, we try to bring integrity protection to full-fledged web applications, assuming that the server is compromised, and with acceptable overhead, given also the fact that our implementation is quite unoptimized. So thank you very much, and with this, I'm happy to take questions.
Questions? Well, then I have a question. So how do you think Verena can be deployed? How do you think Verena can be used by the web developers and adopted by the common users so
for example, now we have an implementation on Meteor, right? We could, and our plan is to actually make it available. Okay, I mean, it would need some, the code is not ready yet, if you ask me like this, so in the sense that, it's a prototype implementation, so I would like to ensure that it's more robust, but then a developer that implements an application in Meteor that we did could just download the Meteor package of Verena and then plug it in and then use the API that we describe in the paper and that is implemented by our code in order to express the integrity policy of the web application and then secure that application. But of course, Meteor is not the only framework out there that is used by web applications. So yes, the idea would be now that you can take the concepts introduced by Verena, implement them in some whatever other web application framework, and get the same guarantees that we tried to do with our implementation on Meteor.
Okay, thank you.
Jae-An Jung, Microsoft Research, very interesting work. So your hash server for freshness guarantee. So if a device has a capability to produce trusted counter, do you still need a hash server for freshness guarantee?
No, we wouldn't need it. But we were thinking actually about this. But we think that then it might, the hash server stores, for example, the latest hash and maybe also some version numbers and stuff like that, right? And this makes makes it easier for the clients and for the whole protocol to be a bit more efficient. So we could do exactly, provide all the guarantees for freshness with just a simple trusted counter, as you said. But then maybe the overhead of the protocol might be a bit higher. So we would need, for example, longer proofs and stuff like that. So this might affect the usability, then the practicality of the whole system, let's say. So our goal was to design something that can be used like, today, essentially, without, realistically, without affecting, or imposing a lot of overhead in the whole stack. But you're right, it can be done with just a counter, yes.